there's a whole group of problems that are like this. I'm just picking out one. This kind of represents problem number 1 and 2 in your homework. They're not particularly hard, but for some of you, having a place to start and what the problem is asking are two different things. So here's what I want you to consider. Consider a situation in which I've got a smooth surface, but there is a patch of the surface that is rough. This 3 meter long patch has a coefficient of friction of 0.5, kinetic friction of 0.5. I have a box that is traveling towards that section with a velocity of 8 meters per second. Bless you. I believe the box will traverse the section and make it to the other side. I mean, it's possible it won't, but I think I've set it up so it will. I would like to know how fast it's going when it makes it to the other side. Assume the box has a mass of 5 kilograms. Now, this is a style of question, and I want to kind of call your attention to it. Newton's laws tell us about forces and accelerations. That's what Newton's laws can tell us. It can tell us other things, but when we use the force concept model, we're going to be deducing the size of a force or the size of an acceleration, because that's what the force concept model does. It produces two relationships. Now, those relationships might be used to do other things, because we have found like the angle of ramps and the coefficients of frictions. We have found other stuff from that. But the force concept model just produces a couple of relationships. If you look at the information that's presented here, the vast majority of the information has to do with things like initial velocity, potentially final velocity, because that's where the question mark is, displacement, acceleration. These should be familiar ideas to you that are not necessarily directly related to Newton's laws. But because acceleration is among them, you should see a clear connection here. That I could use the force concept model perhaps to come up with an acceleration and then use that acceleration here to deduce a final velocity. That's what this example is about. Recognizing that if we have a system that's going to accelerate, then we can use that acceleration in discussing kinematics. And this goes in both directions. We could have a situation in which I know how fast it's going at the end and use that to figure out what the force was on it. So a problem like this is still using the force concept model, but is also using kinematics in part of the solution. So we're going to do this particular example, but if you've looked at the homework, you realize that question 1 and question 2 are just different versions of this problem. You should try them after this. So let's fire this one up. This one's pretty easy. And you should know where to start this problem, meaning you kind of know what's going to happen to the box. The box is going to make it to a point right here. Oops, nope, right here, where it is on the surface where there is friction. I think that's the only surface that matters. Why don't you work out a free body diagram here for this system? Because I'm going to ask a follow-up question in a minute. So take 60 seconds, draw me a free body diagram. It doesn't take any longer than that. If you're taking longer, you're really, really not paying attention. You should participate. It's the only way I know kind of where you are. But I think there's a downwards arrow, correct? Excellent. So we drew a downwards arrow indicating the weight of the object. And I know why people draw this fourth arrow, but it doesn't make it better. This is the weight of the object, which we know to be 50 newtons. Any question about that? Kilograms, meters per second squared. That's newtons. Somebody didn't know that last night. It's not like it hasn't been said. Be aware. The box is in contact with a surface, correct? That means there must be a force perpendicular to that surface. That means an upward force. And I'm going to do my best to draw that so that it is the same size as the weight, because I don't think there's any other force acting upwards on the object or downwards on the object. So I suspect the normal force is equal to the weight. The box is moving to the right. Any cable connected to the box? Any person pushing on the box? So there should be no force to the right. Although I know some of you drew it, I saw it. However, it is moving to the right. It is sliding across a surface that we know has friction. There should be a force that is resisting the motion of the box as it moves to the right. So I would suspect that you have another force this way that is about half the size of the normal force, because the coefficient of friction is 0.5, and you should call that friction. These are the three forces that should have been drawn and no others. So you all who had four fingers in the air, I don't know what you drew that's going to the right, but there was no reason for that. This system is going to be unbalanced on purpose. It's slowing down. We're even being asked about how much it slows down. We should expect the net force not to be zero. Our next step was to put a coordinate system over top of this. And here's where you may want to adjust your set of steps. I gave you two priorities. And the two priorities were to draw the coordinate system so that the positive direction was in the direction of the acceleration. Or, if you couldn't do that, then to draw your coordinate system to align with the most number of forces possible. If you're looking at that set of steps right now, there may be something you want to add to that. I said to align your system, or align your coordinates, in the direction of the acceleration, not the direction of motion. I would strongly encourage you not to align it with the direction of motion, and only align it with the direction of the acceleration. And I want you to keep in mind, this one is stupid simple, but you can choose any coordinate system you want, and that's fine. The problem works out the same. We could choose this to be our coordinate system. It's more challenging because it's clear to me that the object is accelerating this way. It's slowing down. So if I have a coordinate system like this, then there's going to be a part of the acceleration in the x direction and a part of the acceleration in the y direction. The reason why you align one of your axes with the acceleration is so that the acceleration is all in one direction. This is why you're doing it. And since this is the first one we're doing like this, I would strongly encourage you to take and draw your coordinate system so that one of the axes is aligned with the direction of the acceleration. And I would make that the positive x direction. That makes the other one the positive y direction. And although this one's nice because it's organized with all the directions that are there, it's organized with all the forces that are there, it kind of serves both priorities at the same time. There's a good reason to make this the positive x direction. And we'll explain or talk about that in just a minute. Now, I've chosen my coordinate system based on the two priorities. The next thing I'm supposed to do is apply Newton's law. Here's where this comes into play. We purposefully set this up so that when we go to apply Newton's law, we can make one of them zero. The other one is ma, but the other one's zero. It is not accelerating up and down. It is only accelerating left to right. By choosing an axis that is balanced with that idea, that means your acceleration is only in one dimension. If we had chosen a different axis, then this would have to be ma in the x direction and ma in the y direction. There will be times when we will not have a choice and we will have to do that, but that is way more difficult. So whenever you can, you try and use the priority that I gave you. That way this one is zero. Now that that's done, everything else is exactly the same as before. Net force in the x direction, I see only one force in the x direction, that's friction. And that equals ma. In the y direction, I see two forces. I see normal minus weight, and that equals 0, so normal equals 50 newtons. Now, if I want to use Newton's laws, well, Newton's laws have brought me to here. That's it. Now, to make this useful, I'm trying to figure out how fast the box is going after it traverses the distance. So I want to find a way to use what I have here to make that happen. When I look, I see that I have the initial velocity of the box, 8 meters per second, and that it traveled 3 meters across the rough patch. That is not enough information to figure out how fast the box is going, but if I had the acceleration, it would be. Newton's laws can either tell us the size of the force or the size of an acceleration. Seems to me that we have a reasonable way of figuring out the size of the acceleration, and that's what you should be doing now. We can figure out the frictional force, because friction is equal to mu times the normal force, which is 0.5 times 50. Looks to me like the frictional force is 25 newtons. Now that I have the frictional force, 25 equals m times a. Looks like I have a means of getting the acceleration. All I did was use net force in the y direction, definition of friction, and now net force in the x direction to find the acceleration, and the acceleration is clearly 5 meters per second squared. We used Newton's laws to find an acceleration. That's what it does. Now, be careful. A shrewd person will understand that that acceleration is to the left. A person who's not shrewd is going to screw this up. This acceleration is to the left. We've already said to the left is positive x. If you're trying to really nail this and nail this on the next test and quiz and all that, one thing you can put down in your notes is be consistent on positive and negative. If I made to the left positive, then both of these have to be negative, right? The 3 and the 8, because they're to the right. The box slid to the right 3 meters, that's negative 3 meters, and was moving to the right at 8 meters per second, that's negative 8 meters per second. Or, at this moment, reevaluate positive and negative and apply it uniformly to each of the vectors. You can do that too. I'm telling you, pick one of these and go with it. I'm going to pick the one I just did, where I already picked what direction is positive, and I'm just sticking with it. That makes the acceleration positive 5 meters per second squared. So I can get rid of all the force stuff. I just have a kinematics problem now. And v squared minus v naught squared equals 2a delta x. You good? I hope. There's not a whole lot to do here. V squared minus negative 8 squared equals 2 times 5 times negative 3. And you guys can do math. So I don't want to spend any more time with this except to say that v equals plus or minus the square root of 34. We said to the right is negative, so our actual answer is negative root 34, or root 34 meters per second to the right. All right, you have to interpret our answers correctly. So, a Newton's second law problem. This is example number 1. It is a combination of both kinematics and Newton's laws. That's a reasonable set of things that I think you should be able to do. Not particularly terrible. Are there any questions about this example? So you can imagine a different scenario, maybe one where I tell you the final velocity is 5 meters per second, ask you to figure out what the coefficient of friction is. That'd be the same problem, right? Just working it backwards. That is question 2 in your homework, the baseball player sliding between the bases. So try it. If you want to practice something tonight, practice that, because it's exactly aligned with this. All right, we're going to do our next example, example number 2. And I tried to draw this in second period, and it was terrible. So I'm hoping you guys have the same terrible experience. See, I want a... helicopter? It's a freaking helicopter. Don't give me that. It's a helicopter. It is a helicopter. This is a helicopter. It's a helicopter. Don't make fun of my helicopter. It's a helicopter. It's a helicopter. You know why? Because I labeled it helicopter. So now it's a helicopter. All right. Stop making fun of my helicopter. You're making me feel bad about myself.
Sorry. You're not an art teacher.
I am not. All right. A cable is attached to a block, and the other side of the cable is attached to the helicopter. The helicopter is going to lift the 25 kilogram block upwards with an acceleration of 2 meters per second squared. I'd like to know the tension in the cable that lifts this block. Again, the helicopter is connected to the block with this cable. The helicopter is going to attempt to lift the block upwards with an acceleration of 2 meters per second squared. I would like to know the tension in the cable. The truth is there's going to be 3 different problems here. There's the acceleration upwards to get to running speed. There's the time that the helicopter is moving at a constant speed upwards. And then there's a time where the helicopter slows to a stop. So 3 different problems. We're doing problem number 1. So this one is the easiest. Well, the first 2 are pretty easy. Try them. Find the tension in the cable. I'm sad. 300 newtons. So did you draw a dot representing the mass? Did you draw a downward arrow representing the weight of the mass? Because that's where we would start, right? Downward arrow. I'm not changing any procedures here. And this is 250 newtons of weight. I am pretty sure that the only way this thing accelerates upwards is if the upward force is greater than the downward force. Correct? These are unbalanced systems. So I'm putting it greater upwards. That's normal. Well, no, it's tension. Tension force. I'm going to put a coordinate system, but I'm only going to worry about one, the y direction. I don't think I have to worry about the x direction. I'll make that the positive y direction. There's nothing going on in the x direction right now. Are we good to leave that out? I am. Remember, this only serves us. It serves our solution. When I write this, I'm saying the net force equals ma. I see 2 forces. I see tension minus weight equals ma. Mass is 25, acceleration is 2. Any question about that? Seems pretty clear. T's got to be 300. Don't be shocked by this, but if I asked you what the net force on the helicopter is, you should say 50. That's the net force on the helicopter. Net force equals ma. The mass is 25, the acceleration is 2. This is the net force on the helicopter. I'm sorry, net force on the mass. Everybody agreed? All right. Now, I don't think this one warrants any work. If the helicopter reaches the desired speed and then begins to go upwards at a constant velocity, tension's 250, right? Net force would have to be 0, so the helicopter rises at a constant velocity, tension would have to equal weight. But when the helicopter reaches its altitude that's going to cruise at, it needs to slow to a stop, right? So during that time, the acceleration is downwards at 3 meters per second squared. What would be the tension in the cable now? This is a new problem. Perhaps start by drawing a free body diagram. I'll leave one of them up there, but what would you do now? Now, for those of you who are having trouble, and those of you who got it right, great. It's 175 newtons. When you draw your upward arrow for tension, did you draw it greater than, less than, or equal to the 250? Less than. The cable still pulls up. it just doesn't pull up as much. It allows the weight of the mass to slow the mass down. So you apply less tension in the cable. You could still make upwards positive if you want. I said to make the direction of the acceleration your positive direction, but you could make the upwards direction positive y still. You just have to be aware that that means it's accelerating downwards. So I could still do t minus 250 equals 25 times negative 3 because it's accelerating downwards. Or make downwards the positive direction and have 250 minus t equals 25 times 3. These are the same equation. I just multiply them through by a negative sign. You're going to get the same answer. So choosing up or down to be positive or negative doesn't change your answers. Still tells me the tension is going to be 175 newtons of force. There's a limit here, meaning you can only slow the mass down at some maximum, right? The string can't push down on the elevator. It can't push down on the box, can it? So the maximum downwards acceleration is 10, the acceleration of gravity. It can't accelerate it downwards any faster than that because that's what's pulling on the box. It's a limiting factor. So be aware, in problems like this, there are limiting factors. Again, the string can't push down, just like normal forces can't pull. These become limiting factors. All right, that's example number 2. There's a problem in your homework just like this. It's an elevator problem. All right? Ready to see the next one? If you want to see where the AP exam is likely to spend most of its time, that's right here. Oh, how they love their inclined plane problems. Inclined plane problems are a big part of the exam. There's just no way around it. They love them. There's one on last year's exam. There will be one on this year's exam. 60% of you are very likely to have to do an inclined plane problem of some sort. So I think we start with what I feel is probably the most straightforward way to go. And this is mostly for the people who need to have another practice, another go at this. Let's say that this is a frictionless surface. And if you feel like you've got a handle on this, then make it a surface that does have kinetic friction. That's 0.25. Pick which one you think you can handle. All right? Let's say the box has a mass of 5 kilograms and is inclined 40 degrees. The box is given a tap so that it is moving already. And it's given a tap so that it's moving down the ramp. All right, so somebody just tapped it. What is the acceleration of the box? And is it up or down the ramp? You pick which one you want to do. Either do it frictionless or do it with friction. If you're just barely tasting this, then do the frictionless one. If you got a good handle, do the one with friction. And if you really have a strong handle, then don't do it with 5 kilograms. Do it with M, because the mass doesn't matter. And you'll be able to see that. But we have only 4 minutes, so whatever you're going to do it quickly. We will work out both of them, but you should be about done. If you have no friction, this is what you drew, right? This is what you drew? If you had no friction? And if you had friction, you drew this. So I clearly said it's moving down the ramp. These are your two options. Did you make your coordinate system aligned with the ramp, since that's the direction it's accelerating? And did you pick one of these directions to call positive? I would pick that one to call positive. This is where the 40 goes. So we'll have to pick this up tomorrow.